Alright, so we are going to do 1.2 and 1.3 today. 1.2 is going to be really short. It's just 2 vocabulary words that we've got to talk about, and then we'll do 1.3. Before we get started, I want you to think about these bell word problems. So take a second, in your own words, define accuracy, and then answer number 2. Alright, go ahead and pause if you're still working. You probably are. We're going to get back to the definition of accuracy, so keep that in your brain or written down close to you. Number 2, an unknown problem in which the exact distance is 5.2 miles. Suppose you determine the distance to be 5.1 miles. Does the difference of 0.1 miles really matter? So we're thinking, is there an instance where that 0.1 miles could really make a difference? And I think there's a lot of situations where it could, especially if we're talking about if we're traveling somewhere, we could miss our destination or come up short, actually, since we determined it to be 5.1. Maybe if we're walking somewhere or we're participating in some sort of race. I know 5.2 miles is not a race length, but let's say we are, it is. You come up short if you don't do that 5.2. So that's important to think about when you're thinking about accuracy. So today's agenda, 1.2 mini lesson, 1.3 lesson, and then homework with any extra time. Remember, your homework is due either 9/11 if you're odd or 9/12 if you're even. Our objective, so for 1.2, we're just talking about accuracy and precision, differentiating between the two. When we get to 1.3, we're going to start on these objectives. I'm not sure if we will get all of these objectives done in this video or if next class we'll talk about them. But we're talking about transformations, basically. So first, precision. This is our book's definition. When we're measuring, precision is the level of detail of the measurement. When performing calculations with measurements, the calculated value is no more precise than the original measurements. What this means is that if you've taken chemistry or you're taking chemistry, you've probably talked about this. When you are supposed to be precise, you want the amount of decimal places, basically, to be the same as whatever you started with. So if your problem, the most decimal places your problem gives you is 2, your answer should have 2 decimal places, which will mean that you are going to round. Accuracy. So our book's definition, accuracy refers to how close a measured value is to the actual value. The accuracy of measurements may affect how you decide to state answers when performing calculations with them. So accuracy is how close you get to the actual answer of the problem. So this might be more decimal places. This refers to that problem in the bell work, 5.1. That's close, so it's pretty accurate, but it is not completely accurate because it's not the right distance. So you got to be careful when thinking about accuracy and precision. You want the most accurate answers you can get while also being precise, if that makes sense. So you want your answers to be as close as possible while also staying within that constraint of the decimal places. Alright, so here's a little video about accuracy and precision we can watch.
Thanks for stopping by. Today we're going to talk about the difference between accuracy and precision. Accuracy and precision help inform our knowledge when taking measurements. Accuracy refers to how close something is to the target or actual. Using a target to illustrate, consistently hitting near the center would be accurate. Using another example, if we were to use a scale to weigh a 20 kilogram dumbbell 3 times, and the scale read 18.95 kilograms, 21.22 kilograms, and 19.81 kilograms for each respective weighing, we would say that scale is accurate. Now let's jump to precision, and then we'll bring it back together. So precision refers to how consistent our results are, regardless of how close to the true value they are. Using our target example, if we hit this area of the target on every shot, then we are precise. Using the scale in a 20 kilogram dumbbell example, getting measurements of 23.11, 23.09, and 23.12 for the 3 trials would tell us our scale is precise, just not accurate. It's consistently inconsistent. So let's do a quick review and comparison. Accuracy is measuring near the true value, while precision is getting consistent measurements or results. Let's use the target for some more examples. This would be accurate and precise. All the points are close together and average around the true value. This would be accurate but not precise. The results are around the true value but not consistent with each other. This would be precise but not accurate. All the results are close together but not consistent with the true value. And finally, this is neither precise nor accurate. This is pretty much how it looks when I'm shooting. No consistency, not equidistant from the center, just random. Right? It's important that measuring devices are both accurate and precise, whether it be in research, construction, engineering, or even in your home. If they're not, then results for measurements will be misleading at best and fatal at worst. I hope that helps you understand accuracy and precision a little more, and you can comment below if you have any questions, and be sure to subscribe for more educational content.
Alright, so if I can get out of this screen. So what he was saying, again, we want to be accurate and precise. We want our answers to be close to what, or our measurements to be close to what the actual measurement is. We want our answers to be as close as possible to the actual answer, but we also want to be precise. So every time we do it, we want to get the same or close results. We also want to make sure we're following that decimal place rule. So, discussion. Does rounding affect the accuracy or precision of your results? So, do you think rounding affects your accuracy? If you round within the problem or if you round your answer? Okay. Giving you some time to think about it. Rounding does affect the accuracy and the precision. If you round too much, within the problem especially, then you're throwing your answer off even more and making it less accurate. Precision, if you round incorrectly, you can make it not precise because you can make your significant digits or significant figures wrong. Alright, does the unit of measurement affect your results? So let's say we're talking about distance again, and we're going a far distance. Does using miles versus feet affect your results? So I would say yes, obviously. We want to use what's appropriate. So if we're going 5.2 miles, I don't want to use inches for sure. And I really don't want to use feet because that's going to be a really large number also. But if we're talking about something really small and we try to use feet, then we're not going to get the most accurate measurement because it's just not going to get close enough. Especially when looking at something like a ruler, you want to use the smallest measurement possible. All right, and finally, how can you tell if a tool of measurement is accurate? So if we're using a tool to measure something and we want to see if it's accurate, well, we got to test with something that we know the measurement of. So like the example in the video, the 20 kilogram pound or weight, since we know it's 20 kilograms, you want to use the tool and make sure it gets close to the correct result every single time. Alright, let's do this example together. You use a centimeter ruler to measure the dimensions of the jewelry box shown. Estimate the volume of the jewelry box. Let's see. Oh my goodness. Okay, so looking at this picture, I see that my length is 22.5 centimeters. My width is 11 centimeters, and my height is about 6.5 centimeters. So 22.5, 11, and 6.5. Let me pull up a blank. There we go. So my length is 22.5. I already forgot my numbers. Width is 11, height is 6.5. So if we're trying to find volume, that's length times width times height. So we're taking 22.5 times 11 times 6.5. I'm going to use my calculator to do this. And I'm going to get that my volume is 1,608.75. And now, because I want to be accurate and precise, so this is pretty accurate because my measurements were really close on those centimeters. And it's to get the precision, I want my decimal place to match what I started with. So if I started with one decimal place, the tenths place, I want to round my answer to the tenths place also. So that would be 1,608.8. And then my units are centimeters cubed because I'm multiplying centimeters 3 times. All right. So that is it for 1.2. Now, 1.3, I want you to go to page 29 in your books and work with a partner on the Explore It problem. So you should be about the same area as somebody next to you. Pause the video, work on the Explore It problem. All right, so you should be back now. We're going to match these. So when we're trying to name our function families, this one is going to be the easiest one for me because it's the one I've seen the most. I know that that's linear. Okay, I'm going to move this over here now. Okay, now this one might have confused you. You might have thought linear, which it is linear. It's a line. However, we're going to call this a constant function because it's just a constant. There's only y equals 1 for that. Okay, now these, you should have said quadratic. The little v shape is your absolute value. And this is your exponential, and hopefully you remember that's exponential growth. All right, so basically what we just said, function families. Functions that belong to the same family share key characteristics. The parent function is the most basic function in a family. Functions in the same family are transformations of their parent function. So remember how I said we're talking about transformations? So we have this little picture here. You have this in your book. A constant, f of x equals 1 is your parent function. Linear, f of x equals x is your parent. Absolute value, f of x equals the absolute value of x. And then quadratic, f of x equals x squared. And then we can look at our domain and range, and usually when we transform them, we might change the domain and range a little bit, but we're going to follow the same patterns, which we'll get to later. All right, so example 1, identify the function family to which f belongs. Compare the graph of f to its parent function. So looking at this, it's that V shape. It's the two lines that meet in the middle. So I know it's absolute value. When I'm comparing it, so let's go back to this picture. My absolute value parent function hits at the origin. Up here, or this example, it's hitting at y equals 1. So I know that it is at least a translation up. It also kind of looks like maybe it was vertically stretched. So if you took a rubber band and you stretched it vertically, it tends to get thinner, right? So this one looks like it might be a vertical stretch. All right, self-assessment. So answer your self-assessment problems, pause, and then come back and we will answer. All right, this first one. I can tell that this is linear. It's just a straight line. Compared to its parent function, it is shifted up 2 units because it's not going through the origin anymore, but it still has a slope of 1. So we haven't stretched or shrunk. This next one, this is quadratic, that U shape, and it's shifted over to the right 3 units. So that origin, again, I've moved that point over. And then thinking about the quadratic function, hopefully you were able to see this. This looks like a vertical shrink, so it looks like I squished it from the top down. All right, describing transformation. So transformation changes the size, shape, position, or orientation of a graph. The first transformation we're going to look at is a translation. It shifts the graph horizontally or vertically, but it does not change the size, shape, or orientation of the graph. So nothing changes about the graph except for where it is. So for these examples, we're going to do one using a table and then one using Desmos because I want you guys to get comfortable. So this first one, g of x equals x minus 4. I can already tell that's linear, right? But I'm going to go ahead, find my y value. So if x is negative 2, that's negative 2 minus 4. That is negative 6. Negative 1 minus 4 is negative 5. 0 minus 4 is negative 4. 1 minus 4 is negative 3. And 2 minus 4 is negative 2. So we're going to graph these points. So negative 2, negative 6. Negative 1, negative 5. 0, negative 4. 1, negative 3. And 2, negative 2. And we're going to connect these with a line. All right, now we also want to graph the parent function. That's just our y equals x. Here, let's go ahead and label this. Which is our function that goes through the origin and it has a slope of 1. So that's our parent function, f. So describing the transformation, there are 2 ways I can think about this. I can say that I either went down 1, 2, 3, 4, or maybe you could see this horizontal. I went to the right 1, 2, 3, 4. Either way, you would be correct. Okay, example 3. So we've got the function p of x equals negative x squared. So we're going to go over here in Desmos. So open a new tab in your computer. Do this with me. Go to desmos.com and click Graphing Calculator. So we've got the function p of x equals, which I can type, negative x squared. Now we also want to graph our parent function f of x equals, and our parent function of that is our quadratic, just regular x squared. Alright, so our parent function is the blue, and our new function is the red. You'll copy this into your book, so if you need to pause, go ahead and pause. And then describing this transformation, so from the blue to the red, I'm noticing that it's like a mirror image over the x-axis, right? So the way I'm going to describe that, here, I'll go ahead and draw a little sketch for you. That's my parent function. That's my new function. So describing this transformation, I know that this is a reflection over the x-axis. All right, moving forward, self-assessment. So do these self-assessment problems, pause the video and work on them. You can use Desmos or you can graph it by hand using a table. Desmos might be faster. Alright, so you're unpaused, you've done your self-assessment problems. G of x equals x plus 3. I'm going to go over to Desmos. So f of x, I know is just going to be x. G of x is x plus 3. So from blue, my parent function, to my green transformation, you could have either said that it shifted up 3 units or to the left 3 units. Either one would be correct. Okay? H of x equals x minus 2 squared. So again, I'm working with that quadratic. H of x equals x plus 2 squared, right? Nope, x minus 2 squared. That's why you gotta be careful. All right, again, so from blue to green, I'm noticing a shift to the right 2 units. All right, n of x equals negative absolute value of x, so I'm talking about absolute value. Let's see if I can find that here. Oh, there it is. So that is my parent function, f of x equals absolute value of x. And then we're saying n of x equals the negative version of that, negative absolute value of x. So again, from blue to green, this is a lot like that quadratic example we saw. I'm noticing that this is a reflection over the x-axis. Okay, can you describe the transformation in example 2 in a different way? I gave you both ways. So you can say it shifted up or it shifted right, I think is what we said, or down and right. Can't remember. Because either way, you're taking I was taking my origin point and just seeing where it moved. All right, the second type of transformation is a dilation. When the factor is greater than 1, that's a vertical stretch. So again, if you want to think of a rubber band, if you're stretching it vertically, so up and down, it's getting skinnier when it's greater than 0 and less than 1. So it's a fraction or a decimal between 0 and 1. It's a vertical shrink, so you're compressing it. So you know those videos of the hydraulic press that you sometimes get on TikTok, maybe? That would be a vertical shrink or a vertical compression. You're compressing it. You're making it go down. You're pushing down on it. So looking at g of x equals 2 times the absolute value of x. We're going to do this one by hand. And then the next one using the calculator. So 2 times the absolute value of negative 2. Absolute value of negative 2 is positive 2. That times 2 is 4. Absolute value of negative 1 is positive 1 times 2 is 2. Absolute value of 0 is 0 times 2 is still 0. Absolute value of 1 is 1 times 2 is 2. And then absolute value of 2 is 2 times 2 is 4. So plotting these points, which I did not set this up right, so I'm still going to have to use the calculator to show you guys. But that's okay. So looking from the blue to the green here, what I'm noticing is that it's like it's being pulled up. Somebody is taking the graph and pulling it up. That is a vertical stretch. You're stretching it vertically. And I can see that that works. That factor of 2 is greater than 1. So that's exactly what we said. Because that factor of 2 is greater than 1, it's a vertical stretch. All right, next one. So I lied. We're just going to use the calculator. 1/2 x squared. So I'm working with quadratics. So I'm going to have x squared as my parent function. And then 1/2 x squared. So from blue to green, my parent to my transformation, it's like somebody is hydraulic pressing this graph. They're pushing it out. So this would be a vertical compression. And again, you can see that factor of 1/2, that's between 0 and 1. So that's how I know it's a vertical compression or a vertical shrink. All right, graph this function and its parent function. So 3x. Oh, this is self-assessment. Pause the video, do the self-assessment problems. You can continue to use Desmos, or you can graph by hand. It's up to you. All right, so you should be unpaused. You should have your answers unpaused. So we've got our new function, g of x equals 3x. Now this one, linear, is a little more difficult to think about, but if you want to think, if I took that blue line, I grabbed it at the top, am I pulling it up or am I pushing it down? And so thinking about that, this right here, if I pull it up, I get here, which I know is a vertical stretch. I'm stretching it vertically. Again, look at that factor, 3. It's above 1, so that makes sense. Okay, 3/2 x squared, we're working with quadratic. Okay, so from blue to green, again, it looks like I'm taking it, I'm pulling it up. That's a vertical stretch. 3/2, don't let it fool you just because it's a fraction. That is bigger than 1. If I type 3/2 in my calculator, I'm going to get 1.5. So, vertical stretch. All right, 0.2 times the absolute value of x, so we're working with absolute value function. Okay, this looks like a hydraulic press. It looks like I pressed down, so that's a vertical compression. Again, 0.2, that's between 0 and 1, so that makes sense. All right, combinations of transformations. So we can use more than one transformation to change the graph. So we're going to use technology to graph this, and I actually did set this one up right. So parent function, since I'm working with absolute value, that's our f of x equals the absolute value of x. Then we're going to graph this new graph, g of x. And please make sure you're practicing with Desmos. You're going to have to pause and move back and forth, and I know that's a little frustrating. But you need to get this practice because you will have access to a Desmos calculator on your state test and maybe other tests in this class. Alright, so describing transformations. First off, I can see from red to blue that I reflected over my x-axis. When I reflect over my x-axis, this point will still be at my origin though. That is like the mirror part. So then I gotta think, well, to get from here to here, I had to shift to the left 5 and down 3. So I've got a reflection over the x-axis, a translation left 5 and down 3. All right, example 6. We've got this function in the graph, or in the table. I'm going to go ahead and graph that. So I have the point 0, 8, 0.5, which that's a little awkward, but between 0 and 1, 20, 1, 24, 1.5, 20, and then 2, 8. So looking at this, I see that that makes a quadratic function. And then estimate the height after 1.75 seconds. So that would be about right here. So I would say my height is going to be about 15. So at 1.75 seconds, it's going to be about 15 feet. All right, self-assessment. So do these problems, pause, and then come back and check. All right, negative 1/4 x plus 5. That is a linear function. That's just got x. So negative 1/4 x plus 5. So this is what my graph looks like. Describing the transformation. So first thing I'm noticing is that it's like I did the hydraulic press, and that's what makes me think of it. If it helps you, it helps you. If it doesn't, it doesn't. But if you think somebody's pushing down on it, that's a vertical compression. We can also tell that by this number right here. That's between 0 and 1. Now also, it's flipped. My slope is no longer positive. So that means I have a reflection over the x-axis. And that comes from this right here, this negative sign. And then finally, we have a shift. If we think from this point to this point, that is a shift up 5. And that comes from this right there. And you may have said, that it's a shift over. But I don't know that I would have gotten that from this. So I would just stick with shift up 5. All right, next one is quadratic. So we got x squared. That's 3 times x minus 5 squared minus 1. All right, so I can tell that that's a vertical stretch I'm pulling up. And again, we can see that in this number that's being multiplied by the squared part. It's greater than 1, so that makes sense. Okay. I also see that I'm moving my point down 2 and to the right 5. So I've got a shift and I said 2 and I meant 1 because that negative 1. So that comes from there. And then that comes from there. And you may remember this from Algebra 1 or geometry. You have done this before. All right, and then finally, absolute value 2x minus 3. So we're working with an absolute value function. All right, looking from blue to green. I can tell that I pulled it up. That's a vertical stretch. And that's coming from what's being multiplied by the x. And I can also tell that I'm taking my point right here, my vertex, and moving it down 3. And that's coming from right there. All right, last problem. The table shows the amount of fuel in a chainsaw after X minutes. What type of function can you use to model the data? So I can't graph this, but you can graph it on your paper. But I can see from my graph, or from my table, that my y values are going down by 3 each time, which I know that's a constant slope. I know that's linear. After how many minutes will the tank be empty? Well, if I keep going down 3, the next y value would be 0, the next x value would be 50. So at 50 minutes, the tank would be empty. So again, linear and 50 minutes. All right, the last thing before I go, you guys do have homework. The board is wrong because I changed how we did 1.2. So please look here. Your homework. So we've already done 1.1. Now we're working on 1.3. So anytime you have left in class and then also at home, these are your homework problems. Pages 37 through 42, numbers 1 through 4, 6 through 16 evens, and 34 through 46 evens. If you don't have graph paper, now would be a good time to go invest in some. You can use technology or you can graph by hand. I would practice both. So do half by hand, half using Desmos. Or a graphing calculator if you have one.